Hi, welcome to the Math Informant. We're asked to prove this. We're going to use induction. Here's how. Now that we finally got to the end, let's talk about how we got there. If we go back by induction, you always have to prove the first case. So we start with 1 and test it in what we're trying to prove and see if it's true. So replacing every single one of the n's with a 1, we see that this will become a minus b on the left side of the inequality. On the right side, we replace all of these with 1's. And of course, a to the 1 minus 1 is a to the 0, but a to the 0 is just 1. A was a positive number in the first place. So we end up with a minus b on the right side of the inequality. So a minus b is less than or equal to a minus b. Well, since it's equal to, it meets the requirements of that inequality. Now we have to move on to the next step of induction, which is the nth case. The nth case you assume is true. So we're assuming our original statement is true. And that's what we're going to have to use when we do the n plus 1. So we're trying to show the n plus 1. Take every single n in the original thing that you want to prove and replace it with n plus 1, n plus 1, n plus 1, n plus 1. Although some things cancel, it's best just to leave it this way because that's what you're trying to show at the bottom. So now what we start with in the proof, we say, well, p of n, the nth case, was true. So that's our platform to start with. Same exact thing as above in the nth case. And now we just have to start running. First thing that we did was take this b to the n, the minus b to the n, and just added it over here to the other side. After that, the left side, we needed to get a to the n plus 1 in our n plus 1 case. So in order to make this an a to the n plus 1, we need to multiply by an a. But if we do it over here, we got to do it on the right side as well. So the step that we're using here is simply to multiply by a on each side. So we have an a here and an a here. When the a gets distributed onto each one, we get a to the n plus 1 on the left. And then on the right, be careful, it'll give us a to the n plus 1, and the minus 1 hangs there. And some people are going to cancel this. They're going to say, well, just let those cancel. The reason you might want to wait is simple. Your induction case says, leave it this way. So we're going to leave it that way here and everywhere thereafter. Now that we've got this set up, we're missing on the left side what we needed up here. We've got the a to the n plus 1, but we need to have a minus b to the n plus 1. So from this step, the next step will be to subtract b to the n plus 1 on each side. So we want to do minus b to the n plus 1 for each side. Perfect. Beautiful. One's here, one's over here. Okay, the left side of this inequality is great. It already matches our n plus 1 case. It's the right side that we have to work with. What's our goal? We need the right side to look just like the right side of the n plus 1 case up here. What did we do to get there? Well, the first thing we did is we noticed right here, we could factor out a b to the n. If we factored it out, we're left with the a term, and we're left with a b to the first term, or a b term. We're getting close, we're feeling good, but this isn't very helpful. And the real tricky step here is we argue in the inequality that this guy is less than the a to the n term. All the other stuff is the same. This is just a copy paste. But this one, we're saying the b to the n is less than a to the n. And what that's doing is coming from our assumption up here. If b and a are both positive, b is less than a, you can say that b to the n is also less than a to the n. And of course, this is all still greater than 0. Is b to the n really less than a to the n? Here we're going to see on the number line whether that holds. So what we've done is we've picked an a value that's positive at 0.85. And we've taken the b value, which we said had to be a little bit less than that value. Both of them are positive. B is 0.75. And we see here the orange dot right now is A, the blue dot is B. And we want to see what happens as we let their power of n here change. So as we let this change in n, our question is, will the blue dot always stay to the left of the orange dot? In other words, will b to the n always be less than a to the n? Clicking on play, we see that, yeah, the blue dot always stays to the left of the orange. So b to the n is less than a to the n for all of the cases in between 0 and 1. The other case that we should consider, though, is what happens if we go above 1. So we'll reset our n value back and say n is 1, but change the a value and take it up above 1. So why don't we make it 1.2, something small? And we see now the orange dot is just to the right of the value 1, and the blue dot is very close to it, just to the left of the orange, but still bigger than 1. And the question is now, if we let the values for n change the power, does the blue dot stay to the left of the orange dot? In other words, will b to the n be less than a to the n? Once again, clicking play. Yeah, the blue dot stays to the left of the orange dot. So once again, b to the n is less than a to the n. What this shows is that for all cases where both a and b are positive, and a is bigger than b, and the power n is some kind of positive integer, b to the n, the blue dot, will always stay to the left and be less than the orange dot, a to the n. It's this step right here. This is the crux of what gets this inequality to be true. We know if b to the n times a minus b is a certain number, it's going to end up being less than a to the n times that same number, as long as a and b are positive numbers with that inequality holding true in the given information. From here, we are almost home free. What we need to do is rework this to get it back to that n plus 1 case. And there's a couple of ways to do it. I didn't take the most efficient here looking back, but you could still run with this. Here's what we did. First of all, we need to change this guy. We're not talking about a to the n's, we're talking about a to the n plus 1 minus 1. Well, you argued plus 1 minus 1 is 0. Why didn't you just change that? And we said that was because we needed to match. So here, this is a to the n, we can get it to match. We're going to change this one and make him a to the n plus 1 minus 1. Why? Because plus 1 minus 1 is the same thing as leaving us with a to the n. So we just rewrote this guy to make it look like the same power on the one in front. Now that we've got both of these to the same power, we can start to factor some stuff out. Here, the first thing that was factored, at least in this setup, was a minus b. You didn't have to factor this. You could have gone a little bit quicker with it. If we factor the a minus b's out here, we're left with n, a to the n plus 1 minus 1, plus an a to the n plus 1 minus 1 here in this set of parentheses. A minus b is on the outside. Now what we want to do is factor out the a to the n plus 1 minus 1s. If we take them out, we had n of those here, and we had plus 1 of them here. So pulling the a to the n plus 1 minus 1s out leaves us with an n plus a 1. And that's fantastic because that's what you wanted in the end. So we'll shift this around. We're multiplying 3 parts together, but our result has the n plus 1 in the front. So we'll just take him, put him in the front, multiply here a to the n plus 1 minus 1 power in the middle, and on the end we've got a minus b. Left side less than or equal to this by this chain of actions. At the end, you can say QED, quod erat demonstrantem. That which was to be shown originally has been shown. Hope you found this helpful. If you have any tough problems that you'd like to see worked here on The Math Informant, send them to themathinformant@gmail.com.